Welcome back. We are now up to chapter 4 in our trek through the solar system and the universe and all of science that is related to all of the fun stuff we're doing. So we're going to zoom through a little bit here on gravity and Newton and figure out a little bit about some of the concepts around science that we'll be using as we go through here. So let me see if I can share the screen. I think that's the one I want us to use. Yes. And we'll go back to the beginning of this. We'll make sense of the universe. That's a big item for us to do. But some ways in which we're talking about things in space and here on Earth involve motion. Everything is in motion in one way or another. We're all used to the concept of speed. That was a great movie, by the way. Speed is distance over time. So we can have units of meters per second, miles per second, miles per hour, for example. The speed 10 meters per second is related to gravity, so you might remember that. We'll get back to that as we're coming up. Velocity. Velocity is speed with a direction, so 55 miles an hour due north, 55 miles an hour due south, those kinds of things. Acceleration is any change in velocity. Notice it's a change in speed and or direction. We often think of acceleration as putting on more speed, but the truth is, how many of you have just sort of been driving along, going up to Indianapolis at 65, 75, if you're in my car, 85 miles an hour, and you're just going along and it's fine, and all of a sudden you go to a curve? You're not going any faster, but everything in the car seems to go, your coffee in your cup sloshes over. That's acceleration because you've changed your direction. As you're going around a curve, you're accelerating. Even if you're slowing down, you're accelerating just because you've changed direction. So keep that in mind. Gravity is an acceleration. So what it's doing is it is pulling us down. And if we ignore air resistance, everything falls at the same rate. If I drop a 1-pound ball and a 5-pound ball, and if I had a third hand, a 10-pound ball, they would all fall at the same rate. Sometimes heavier things seem to fall faster than lighter things. If I take a piece of paper, for example, it'll just sort of float down. That's air resistance. If you take away the air, if it's in a vacuum, it just right down. Try this for an experiment at home sometime. Take a book, say take a book that has like hundreds of pages so this is like 300 pieces of paper, and take an ordinary piece of paper, let's say this here, and if I drop the two of them, well, the book seemed to fall faster there, if I can pick it up. Then if I crumple up the paper and then drop it with the book, guess what? They seem to hit the ground about the same time, at the same rate. It's because the air resistance in the paper is no longer there, causing an issue along the way. So let me put that poor abused book up there. Pulling us down onto the ground is gravity, and it is pulling us at 10 meters per second squared. What that square means is that if you jump off of a building or you throw a ball off of a building, and after 1 second, if I had my radar gun here, it would say you are going at 10 meters or roughly 10 yards per second. If I clocked you after 2 seconds, you'd be up to 20 meters per second. If I clocked you at 3 seconds, you'd be up to 30 meters per second. That's where that square comes in. You increase by 10 with each second. Different planets, different surfaces have different rates of gravity depending upon how large or massive the objects are. On the moon, there's the same gravity for everything on the moon. If you drop a feather and drop a hammer, which this Apollo 15 demonstration does, they both fall at the same rate because there's no atmosphere, but they fall slower than they do on Earth because the moon is less massive. So the acceleration is not as much. You actually weigh less on the moon, even though you'll have the same amount of stuff. I'm just as blobby on the moon, but I would weigh less. I would probably weigh about 40 pounds rather than 195 or something like that here on Earth. I'm actually proud of 195 because just in my last class I weighed 215. So I've stopped eating French fries because we're on lockdown. So I've lost weight. When we're talking about momentum and force, momentum is how much stuff you have times the velocity. And the net force is a change in momentum. So you could change the mass or change the velocity. Usually it means you're changing the velocity, but you could change the mass as well. So these have an impact, no pun intended there. If I have something that's small but really high velocity, like if I have a bow and arrow, I shoot the arrow doesn't weigh very much, but it can really hit something. On the other hand, if I have something that's big mass, like Zamboni, you don't have to have it going very fast for it to hurt quite a bit along the way. So mass is how much stuff is in the object. Weight is the force of gravity pulling you down. So you weigh a certain amount here on Earth. You don't weigh the same amount on the moon, even though you have the same mass. So weight is particular to what gravity is doing to you. Mass is just how much stuff you are. If you're actually falling, like if you were in the elevator here, unfortunately, it snapped there. See, he's sort of in the air. He's weightless while he's falling until he hits the ground. Then suddenly, boom, it catches up with you. So you don't want to do that as your weight loss program. On the moon, you weigh the same, your mass is less, you weigh less, your mass is the same, your weight is more, your mass is the same, your weight is more, your mass is less. Which one? Well, remember, mass is always the same, so it's got to be one of these two. The moon is smaller than the Earth, so it's going to be B, your weight is less on the moon. Astronauts are weightless in space. It's not that there's no gravity up there. There's gravity all the way out to the moon. That's what's holding on to the moon and why it doesn't just head on out into space on its own. The weightlessness is because of that free fall stuff. As you're sort of going in the space station up there, you're falling back towards the Earth. But instead of hitting the Earth, you're going at just the right speed that the Earth gets out of the way. And instead of falling down, you're falling, but the Earth moves and falls and the Earth moves. You have to do that proper calculation. You don't want to have too much because you might zoom off, and you don't want to have too little because you might fall down. So it's a good calculation to sort of figure out all of this stuff. I had an entire class in my master's degree called orbital mechanics, and we did mostly math related to that, putting up satellites and other kinds of stuff. So these are some good things to remember. Speed is distance over time. Velocity is speed with a direction. Acceleration is any change in velocity, which means it can be just direction. Momentum is mass and velocity, and forces cause a change in momentum. Those are useful things. Mass is how much stuff there is, the quantity of matter. Weight is the force that's enacted on it. And things that are in free fall are in fact weightless, because if you try and put a scale on them, it doesn't work. One of the persons who tried to explain what's happening, remember last lecture we talked about Ptolemy and Tycho and others who were describing where things were, but they never were describing why things operated the way they were. It took Newton to come along and put the experimental data that he was getting and the observational data that he was getting into a framework that helped explain why things operate the way they do. And one of his insights was the stuff that's happening out there with the moon and the planets and the sun is the same stuff happening down here on Earth. There wasn't that difference. There wasn't that disconnect that a lot of the Aristotelians and others said things here on Earth don't operate the way they operate up there. He said, nope, physics is the same everywhere. It's one universe. It's one system of laws and gravity that work on all of this stuff. And his first law was in many ways a cribbing, I won't say a plagiarism so much as a cribbing of Galileo's idea that it's not the natural force or not the natural state of anything to just be at rest. In fact, the natural state of anything is to remain in whatever it's doing. If it's resting, it'll naturally stay there. If it's moving, it will naturally stay there until something outside acts on it. That's actually revolutionary thinking, because if you think of throwing a ball or shooting an arrow or even launching a rocket, they typically curve. Well, everyone thought, well, the natural motion of things is curving, and the natural thing is they all want to stop. Well, Newton said, if you take away the Earth, the natural motion will be just to keep going in a straight line. The reason why they're curving down, the reason why they're sort of going in a parabolic orbit or whatever is happening is because the Earth is acting on them. Take away that and they just keep going. And on the other hand, if it's just sitting there, if nothing else acts on it, it's never going to move. So this is the first law. And in some ways, it should probably be considered Galileo's, Newton's first law. The second law is a basic calculation. Force is mass times acceleration. So you have more mass, you have more force, you have more acceleration, you have more force. And that can actually be mathematically registered as F equals M times A, or F equals MA. You may see that. That's one of the more basic formulations, one of the more basic equations in science. Then the third is that for every force, there's an equal and opposite reaction force. Right now, I'm sitting on a chair and I'm pushing down, thanks to gravity, with about 195 pounds of force. It is pushing up, thankfully, with the same amount. If it was pushing up with more, I'd be catapulted off. If it was pushing up with less, I'd be falling down. So equal and opposite, that happens. So what happens if the force on the Earth is exerting on you is equal and opposite to what you're exerting on it. If you exert a larger force on the Earth, then you're literally pushing the Earth away, or you're actually probably falling through the ground. If the Earth exerts a larger force on you, it's throwing you off, it's throwing you away. It doesn't tend to do that. Earth doesn't tend to do that with too many people. What happens overall with all of these interacting forces is we have a conservation. Energy changes from one object to another, and it can't be destroyed. It sort of goes from form to form, and it goes back and forth. We have different types of forces. We have things that are sort of going faster and slower in space, but the angular momentum is being preserved because here we have more distance, but the velocity is slower. Here we have less distance, but the velocity is greater. So we have one of our elements that's larger and smaller, one of our elements that's larger and smaller. Those balance out all the way along. So that angular momentum is conserved along the way. Some of this is potential and some of it is actual energy. And we'll talk about the difference between that as we go along. The Earth experiences no outside forces, twisting forces, torquing forces, or other kinds of things. So as long as nothing outside acts on it, it's just going to keep doing what it's doing. Now, the truth is we do have some tug and pull in our solar system between the different planets, as well as with the moon and the Earth. So it's not that there are no outside forces at all that are acting, but the forces are in balance, and we don't have the twisting, torquing forces that are yanking it away. If you've ever seen a television show called Space 1999, if you're old like me, back in the 70s, you were watching science fiction, and one of the things is the moon gets pushed out of orbit. Well, it had some great torquing forces. It had explosive forces that pushed it away. It really takes that kind of thing to push things out. So we're just going to keep going and going and going until some outside force acts upon us like this. Now, we've seen already from Kepler, the planets that are closer in go faster, and the planets that are out there go further out than we are go more slowly. If you see a skater who pulls her arms in, she tends to go really fast, and as she puts her arms out, she tends to slow down. Well, think about that again in terms of the number of rotations and the distance of the rotation. By the time I have my arms all the way extended out, that's more than 6 feet, probably about 6.5 feet with my arms along the way. That's a long way to go around in a circle. That's a lot longer than the sort of 2 feet of just my shoulders back and forth as I'm sort of spinning around with my arms in. So I can do more spins if I have less distance. I can do fewer spins if I have more distance. That's rotational angular momentum being conserved there. Energy makes matter move. It's conserved, but it can change in form and transfer from one object to another. 3 basic types of energy: motion, kinetic energy. So when you're moving, that's kinetic energy. We have radiative energy. That's light that's coming to us, the energy from the sun. And then we have stored energy. Actually, stored energy, we think of like the gasoline, we're going to burn it. So when we burn it, when it goes through the engine, that stored energy is being changed into kinetic energy so that the wheels go round, for example. But one of the things that happens is, see, I'm holding this bottle up here. This is actually stored energy. Why? Because if I drop it, the stored gravitational energy changes into kinetic energy. So, and that's how elevators work. You have stored energy and kinetic energy trading off on each other. There are all sorts of ways in which the energy can trade off. Thermal energy is the collective kinetic energy, remember this is motion, of particles. So the particles in the air, the particles in water, the particles in whatever it is that has a temperature are all moving. There's nothing that's sitting still. The higher the temperature, the more those particles are moving around. So the temperature is the average of all that motion stuff that's taking place there. And we can measure that by different scales. We have Fahrenheit that we're mostly used to here in the United States. Water freezes at 32 and boils at 212. That's at sort of sea level. When you change the atmospheric pressure, those things can change a little bit too, but we won't pay too much attention to that for our purposes in this class. Celsius scale decided, well, no, that's clunky. So we're going to do 0 where it freezes and 100 where it boils. Kelvin said, well, even that's clunky because down here to absolute 0, it's still a weird number. So Lord Kelvin said, oh, we're going to start with this at 0. And that makes the water freezing and the water boiling points at clunky numbers. But the thing is, these only really apply on the surface of the planet when we are at sea level. Those will change in different environments along the way. In fact, if you take a car up to Colorado, especially if you drive up into the mountains, you may get a lot of knocking and other things happening in your engine because the temperature at which the stuff inside your engine operates is going to be different under the different atmospheric pressures that are there. So that has an impact on things. But just note that these are temperature scales. One little tiny sort of trivia thing. Notice the K here for Kelvin doesn't have the little degree thing. We have degrees of Fahrenheit, we have degrees of Celsius, but we don't really have degrees Kelvin. The Kelvins are just Kelvins. They're not degrees of Kelvin. So that's a little thing. I sometimes see Star Trek make that mistake. It's like it's 270 degrees Kelvin. It's like, it's not degrees. They could have hired me and I could have been a script consultant and I could have told them, but no, they turned me down. So when we're looking at this, temperature is the total kinetic energy of the particles. That means it depends on what the temperature is and the density. If I stick my hand in an oven to grab the pizza that I'm heating, and it's 400 degrees Fahrenheit, 200 degrees Celsius. I can stick my hand in there, grab the pizza and go, and my hand is just fine. If I try to grab the boiling egg out of the 212 degrees Fahrenheit, 100 degrees Celsius, roughly half the temperature, I stick my hand in the boiling water, what happens? It's bad. Yeah, why? Because it's not just the temperature. There are so many more particles in the water than there is in the air that you don't have to have as much temperature. You don't have to have as much total kinetic energy in those particles themselves for it to be a much hotter thing. If I stick my hand in that oven in the air, it's 400 degrees, my hand is fine. If I brush up against the iron or the steel or whatever the oven is made out of, that hurts because that's a lot denser and it's also the same temperature. So it's like, yep, I paid for that pizza. So microwave for me. When we're talking about gravitational energy, again, as I talked about, I'm holding the bottle up. When I drop the bottle, gravity takes over, it turns it into kinetic energy. If I throw the ball up in the air, it's moving at a certain point. It's going to balance out between the motion. It's going to stop, and then it's going to start coming back down again along the way. So as it comes back down, it has less gravitational potential energy and more kinetic energy. On the way up, it has less and less and less kinetic energy and more gravitational energy. But those two balance out on the way up and on the way down. What goes up must come down. That's one of the things to keep in mind when I see people sort of out in the country and they sort of pull out a rifle or something and start shooting just in the air. It's like, you know, those bullets are going to come down somewhere. So be safe. Be safe with stuff like that. Because yeah, physics will tell you be safe with stuff like that, because that's a lot of energy that's in there. But gravitational potential energy is out in space as well. We see that when a cloud of material contracts under its own weight, gravity pulls everything together. It has less gravitational energy once it's pulled together, but now it has more thermal energy. It has the heat sort of heats up and heats up and heats up. Whereas here it's all dissipated, now it's more concentrated in that area. And of course, mass and energy are related to each other as well. This is Einstein's famous equation, E equals mc squared. E equals energy, m equals matter, and c is our speed of light. So, and again, I think I've mentioned in a lecture before, that would be a good number to remember. Speed of light is, come back here. Speed of light is 186,000 miles per second, or 300,000 kilometers per second. So let me just type the C equals 300,000 kilometers per second, or 186,000 miles per second. So when we're talking about c squared, we're talking this times itself. And when we're looking at this equation, it's actually in meters, not in kilometers. So it's a much bigger number than we're dealing with here. So, but even this, 300,000 kilometers per second, 300,000 times 300,000, we're getting 900 billion kilometers. And then when we transfer that into meters, we're talking trillions of meters, which means you only have to have a really small amount of matter to become a really big amount of energy. That's why nuclear weapons are as destructive and damaging as they are, because in fact, they are taking sometimes only a couple of pounds of something like uranium or plutonium. But it's not just uranium and plutonium that does this. The process in the sun is hydrogen. Where's a lot of hydrogen? Water, H2O. That's being fused together, and that is also operating. You only have to have a little bit of hydrogen to get a lot of energy when you're doing a fusion process that's there. So energy is not created or destroyed, but can be changed in its form, kinetic to potential to radiative, and can really transfer back and forth between energy and matter according to E equals mc squared. The total energy content of an isolated system remains the same. That's the real problem, because almost every system leaks energy in some way. That's why we don't get these perpetual motion devices, because they're always leaking energy in some way. There's no way to keep it perpetually going without putting some new energy in, because some of it's leaking out. People have tried for centuries to try to figure out perpetual motion. When we're looking at gravity, gravity, as we talked about before, potential gravity, other things, everything in the universe is attracted to everything else mass-wise. So if the universe only had two sort of iron balls that were each 2 pounds each, they would both be attracted to each other. If they were in motion, they'd probably be going around each other like this, but they are directly proportional to the product of their masses, which means the larger they are, the more attractive they are. The closer they are or the further away they are, that makes a big difference too, because they are inversely proportional to the square of the object. And that's where we get this clunky equation down here along the way. What that means is that the sun, being so much larger than anything else in our solar system, is the most attractive thing. But some things are enormously far away, and the further and further and further away you get from things, it drops off at the force of a square. So if you're twice as far away, it's only 1/4 as attractive. If you're 3 times as far away, you're only 1/9 as attractive. If you're 10 times as far away, you're only 1/100th as attractive. Well, guess what? Neptune is 30 times further away from the sun than the Earth is. So it's only 1/900th as attracted to the sun as we are. So it's going in a much slower orbit along the way. There are different kinds of orbits. We can go around in a bound parabolic orbit. That's what the planets are doing. That includes if you happen to have one that's a perfect circle, we would still call that a bound elliptical orbit. Because remember, an ellipse is just a special kind, or a circle is just a special kind of an ellipse. You can have some that come in, whip around, and go back out pretty much on the same trajectory. We call that a parabolic orbit because back here and back here, these lines will be mostly parallel. One of the ideas of parabolas is that as you get to infinity, they are parallel. We might also have a hyperbolic orbit where it sort of comes in this way and goes in that way, and it's a mirror reflection of what happens there, but it's not sort of in one direction and out exactly the same way. So we have ellipses, that includes circles, parabolas, and hyperbolas in those different ways. We can then take Newton's equation back here. See, this clunky thing is actually not as intimidating as it might seem. This just means the force of gravity. This g here is just a number called the gravitational constant to make the numbers work. These m's are the masses of the two items that are attracted to each other, say the Earth and the Moon, or the Sun and the Earth. And then the d is the distance between them. So if you make this d bigger, then the gravity is less. And again, that's less by a square. If you make the masses larger, the gravity is more because they're on the top of this equation here. So if we take Kepler's equations and put our gravity in the middle, remember Kepler said how long it goes around is related to the distance. Well, Newton figured out, hey, I can put my little equation in here, and that helps explain things on an astrophysical basis along the way. So orbits go around, they have gravitational and kinetic energy. They're moving, so they have kinetic energy. They're also bound to the sun, so they have gravitational energy. When they're closer to the sun, they're going faster. When they're further away, they're going slower. So we have our energies being sort of traded back and forth there. But orbits don't change spontaneously. They just, again, keep going in the way they're going unless an outside force acts on them. That's one of those Newtonian laws. You can change an orbit. Here, a comet was going on, it looks like one of these hyperbolic orbits around the sun here. As it's sort of going through, minding its own business. Uh-oh, it strays a little bit too close to Jupiter. It's going too fast. Notice this little wedge right here. From here to here is another very smooth, very sort of flattened, but still very much a hyperbola here. And then it still is inward to the sun, so it sort of goes around like this now. Its orbit has changed. That happens to different objects as they get too close to something along the way. That's called a gravitational encounter. And sometimes a comet or an asteroid will get too close to Jupiter or one of the larger planets and get its orbit changed and then later crash into that planet. We have some things crash into our planet too sometimes. This is what's happening. We can also have friction or atmospheric drag. There are no atmospheric things happening out in the solar system, but if things come into our Earth or come into Jupiter's atmosphere or another planet's atmosphere, that can change what happens as well. If we want to get off the Earth, we have to overcome the power of our gravitational forces. So if I throw something, it falls back down. If I throw it even harder, it falls back down a little bit further. So you have to figure out how much force do I have to throw something for it to actually escape. We have to roughly match 11 kilometers per second from sea level, which is about 40,000 kilometers. So we're going to talk 25,000 miles an hour. That's why you have to get those rockets that launch from NASA up to speed really, really fast. So you have huge, huge amounts of force that are on those rockets pushing up, and they will typically use in a sort of typical chemical rocket that's launching stuff up there, about 740 pounds of fuel for each 1 pound of something they want to get up there. So it's a lot. It takes a lot, but it only takes a couple of minutes before it's off and on its way. The moon is not in a gravity-free zone. The moon actually is attached to the Earth because of gravity. The Earth is attached to the moon because of gravity as well. They are mutually attracted to each other, and they're in fact going around each other. Now it looks like the moon is going around the Earth, but in fact the Earth is responding a little bit back and forth as well. So when the moon is over here, the Earth is over here. But when the moon is over here, the Earth is a little bit over here. So as the moon looks like it's going like this, the Earth is in fact going like this as well. They're going around their mutual center of gravity along the way. But as the Earth pulls on the moon and the moon pulls on the Earth, one of the interesting things that's also happening is the moon's gravity pulls on water differently than the solid. Our tidal friction has slowed the moon's orbit, or slowed the moon's rotation as it's going around. So it's always facing the same way. The same face of the moon always faces us. We never see the far side of the moon as it's going around. But as the moon is going around like this, it's pulling on the water. The water's pulled, the rest of the Earth is pulled a little bit, but not as much, and it actually leaves water behind on the other side. So we have a high tide on both sides of the planet at the same time. And as the Earth is spinning, we thus get high tides twice a day everywhere on the planet, depending upon where the moon is in terms of where the sun is, as well as the geography, the particular geography of the area of our Earth. The tides can be really high or really low. The Bay of Fundy in Canada, for example, has huge, huge tides. And I will try to post up a video of that. In fact, I'm going to write that down right now on this. We will want the Bay of Fundy video, so you can see the tide roll in and roll out there. It goes up and down 6 stories. Most of the time, if you're in Florida, you're going to get a couple of feet up and down at most. But there it goes up and down 6 stories. In part, that's because of the tilt of the continental shelf there as well. But I will post that video up so that you can watch that at your leisure. And I will see you again on Zoom in perhaps our live meetings, or also coming up chapter 5 next week.